Praise be to Allah. By time indeed, mankind is in loss, except for those who have believed and done righteous deeds, and advised one another to truth, and advised one another to patience. In this episode, we will start explaining the details of differential protection for bus bars, beginning with low impedance differential protection. So stay with us. It's a moment, and then it's a moment. The bus bar is among the most dangerous elements in the electrical system. A fault requires disconnecting all power sources and loads. Initially, bus bars had no specific protection, relying on feeders. As systems evolved, dedicated protection devices became necessary. Failing to detect a bus bar fault can lead to its loss and potentially burn down the entire station. Bus bars are crucial in protection systems, demanding caution in operations. Initially, they lacked specific protection, relying on feeders. As systems evolved, dedicated bus bar protection became essential, especially in large setups, while backup suffices elsewhere. Undetected bus bar faults risk loss and station fires due to interconnectedness. To mitigate, major stations section bus bars, allowing fault isolation without full disconnection, maintaining stability. Bus bar protection is for large systems. Backup protection is enough for others. Failing to detect a bus bar fault can lead to its loss and cause the entire station to burn down, as all system elements are interconnected. Major stations divide bus bars into interconnectable sections. This avoids full station disconnection during faults. Faults isolate only the affected part, keeping others stable. This minimizes disconnection. Important parts should be fed from multiple sections for continuity. Major stations, anticipating problems, divided a single bus bar into sections that can interconnect. This prevents disconnecting the entire station if a fault occurs. A fault on one part can be isolated, keeping the rest stable. This reduces sections needing disconnection during a fault. Important station parts should be fed from multiple bus bar sections to ensure continuity if one section disconnects. Common bus bar systems in stations include single bus bar with section, double bus bar with coupler, and 1.5 bus bar. Protection methods vary by bus bar type, design complexity, and importance. It should be noted that important parts of the station should be fed from more than one section of the bus bar to ensure continuity in case that section is disconnected during a fault. Among the most common types of bus bar systems used in electrical stations, the arrangements of the bus bars inside the station are as follows. The first type is the single bus bar, the second type is the single bus bar with bus section, the third type is the double bus bar with bus coupler, and the fourth type is the 1.5 bus bar. There are various methods used to protect the bus bar depending on the type of bus bar, the complexity of its design, and its level of importance. However, in all cases, bus bar protection must generally be characterized by high reliability and a strong ability to distinguish faults, in addition to quick disconnection to prevent the entire station from going offline. Most bus bar protection methods will rely on Kirchhoff's current law, which states that the sum of currents entering a point must equal the sum of currents leaving that point, and in our case, that point is the bus bar. This law applies in normal conditions or external faults where currents entering the bus bar equal those leaving it. If a special CT is installed for bus bar protection, note that placing the line differential CT red after the circuit breaker and the bus bar differential CT blue before it creates unprotected areas known as the dead zone where no basic protection detects faults. Moving the line differential CT between the bus bar and circuit breaker creates another unprotected area. If a fault occurs here, line protection activates, not bus bar protection. If line protection disconnects all circuit breakers, the fault remains fed from the bus bar, which is incorrect. Moving all CTs after the circuit breaker introduces a new problem. A fault here, undetected, forms a dead zone. Moving the line differential CT creates another unprotected area. Faults here, trigger line, not bus bar protection. If line protection disconnects breakers, the fault remains from the bus bar. Moving all CTs post-breaker causes a new issue. Faults between the breaker and line differential CT activate bus bar, not line protection. If bus bar protection trips all breakers, the fault remains fed from the remote line circuit breaker. This means that if a fault occurs in this area, the line protection will activate, not the bus bar protection. If the line protection operates and disconnects all the circuit breakers on both sides of the line, opening these breakers will not isolate the fault because the fault will continue to be fed from the bus bar, which is incorrect. However, if all the CTs are moved after the circuit breaker, a new problem arise. If a fault occurs in the area between the circuit breaker and the line differential CT, the bus bar protection will activate while the line protection will not. This is because the line protection considers this fault to be outside its coverage area. This means that if the bus bar protection trips all the breakers connected to it, it will not isolate the fault because the fault will continue to be fed from the remote line circuit breaker. Therefore, what we mentioned in a previous episode is that the bus bar protection in this case should send a trip signal to the line differential protection, which in turn will send this signal to the remote insert breaker to disconnect it if the current continues. To separate it if it continues longer, after opening the circuit breaker, current lasts 100 to 150 ms. For a volt 1 fault, circuit breaker 2 at the remote substation stays closed, as circuit breaker 1 at the local substation stops the fault current via bus bar protection. A volt 2 fault requires opening circuit breaker 2 due to ongoing fault current, even after circuit breaker 1 opens. Fault location allows current flow from circuit breaker 2 if it remains closed. Optimal CT placement for protection coordination is line differential CTs between the bus bar and circuit breaker, and bus bar differential CTs after the circuit breaker 4. After circuit breaker 1 opens, fault current continues if circuit breaker 2 stays closed. For protection coordination, place line differential CTs between bus bar and circuit breaker, and bus bar differential CTs after circuit breaker for overlapping zones. With network growth and increased capacities, new high-spec current transformers are needed, installed after the circuit breaker, while old ones remain. Bus bar protection CTs are active only if the earth switch is off or connected under a permanent condition, preventing false bus bar protection if the circuit is incorrectly connected remotely or in a switch into fault condition. Network growth and increased circuit capacities need new transformers placed after the breaker, keeping old ones. Bus bar protection works only if the earth switch is off or connected with a permanent condition on bus bar CTs. If the earth switch is on or connected, it prevents false protection in 2 cases: wrong remote connection with line earth switch connected, or current from cable charging due to nearby circuit induction. Thus, line protection is off if the switch is closed to prevent false operations. Closing the switch shorts the bus bar CT and turns off protection sets 1 and 2 only if the earth switch is off or the earth switch is connected while we are applying a permanent condition on these bus bar CTs. I mean, if the earth switch is in the ON position or the earth switch is connected, this is to prevent false operation of the bus bar protection in the station under one of 2 conditions. First, the condition of connecting the circuit incorrectly from the remote on circuit breaker if the line earth switch is connected, or what is called the switch into fault condition. In the case of current flowing through the charging of the cable due to electromagnetic induction from another live adjacent circuit, the line protection is also disabled if the line earth switch is closed to avoid any false operation, even on the line protection. In summary, if the line earth switch is closed, it creates a short on the bus bar CT and disables line protection set 1 and line protection set 2. Line protection 6.1 and line protection 6.2. The bus bar is considered a gathering and transition area for currents from the generation area or from the grid to the direction of feeding the loads. Notice in this image that under normal conditions, the current entering the bus bar through the incoming circuit breaker, referred to as I1, should equal the sum of the currents leaving the bus bar through the outgoing circuit breakers, which are called I2. I3. I1 equals I2 plus I3, so I1 minus I2 minus I3 equals 0. If a fault occurs on the bus bar, all currents change direction to feed the fault. The vector sum of currents won't be 0, meaning I1 won't equal I2 plus I3, and I1 minus I2 minus I3 equals the fault current. With multiple sources, incoming currents must equal outgoing currents. The difference is the differential current. Low impedance differential protection measures differential and restraint currents. If the differential current exceeds the minimum setting or is greater than the restraint current slope, the relay trips. If a fault on the bus bar is 1 kiloampere from one source, both differential and restraint currents are 1 kiloampere. Plotting this on the differential curve shows it above the operating region, triggering a trip signal. The value of the current between the incoming currents and the outgoing currents is what is called the differential current. The principle of low impedance differential protection for the bus bar is to measure the value of the differential current and the restraint current. If the value of the differential current is greater than the minimum differential current setting, or if the value of the differential current relative to the restraint current is greater than the slope, the relay will issue a trip signal. If a fault occurs on the bus bar itself with a value of 1 kiloampere and it is fed from only one source, then the value of the differential current will be 1 kiloampere and the value of the restraint current will also be 1 kiloampere. If we plot a point on the differential characteristic curve representing the differential and restraint currents, we will notice that this point will lie above the curve in the operating region, which means that the relay should issue a trip signal at that moment. If a fault occurs on the bus bar and is fed from multiple sources, the value will be 7 kiloamperes. The relay will issue a trip signal because the point is above the curve in the operating region. If a trip signal is issued from the bus bar, it should go to a system called the internet reaping, which distinguishes which circuit breakers should trip due to the fault. Assuming the bus bar is divided into 4 zones, if a fault occurs in zone 2, only the circuit breakers for zone 2 should trip, while those for zones 1, 3, and 4 should not. If a fault occurs outside the bus bar, like on the line, all currents entering the bus bar will exit to feed the fault point. This means the differential current should be 0, assuming currents entering are positive and those leaving are negative, while the restraint current would be, for example, 12 kiloamperes. This means that if we assume that the bus bar is divided into 4 zones, if a fault occurs in zone 2, for example, only the circuit breakers associated with zone 2 should trip, while the circuit breakers associated with zones 1, 3, and 4 should not trip. However, if a fault occurs outside the boundaries of the bus bar, such as a fault on the line, all currents entering the bus bar will exit to feed the fault point on the line. This means that the value of the differential current should be 0, because we assume that the currents entering the bus bar are positive and the currents leaving the bus bar are negative, while the value of the restraint current in this case would be, for example, 12 kiloamperes. As we mentioned before, it calculates the total current without considering the direction, meaning it doesn't care whether the current is incoming or outgoing. The current is always positive. When we represent the 2 points on the curve, we will notice that the point falls below the operating curve, which means it should remain stable in the case of external input. We must remember that the bus bar zone boundaries are set by the CT's positions. If a fault occurs on the line, considered external for bus bar protection, it may cause a CT to saturate, as if its secondary is short-circuited. To understand this, we calculate the differential and restraint currents and apply them to the curve. In this example, the differential current rises to 2 kiloamperes and the restraint current becomes 10 kiloamperes. When plotted on the differential characteristic curve, the point falls below. A CT enters saturation, meaning its secondary is short-circuited. We calculate the differential and restraint currents and apply them to the curve to see the outcome. We will notice the value of the differential current in this example rose from 0 to 2 Ka, while the value of the restraint current is now 10 kiloamperes. The point falls below curve. This means it remains stable with external input and saturation limits of a transformer on a non-faulty circuit. This means that it will remain stable in the case of external input, in addition to the saturation limits of one of the current transformers mounted on one of the circuits that did not experience a fault. But the worst case scenario is that one of the current transformers on the feeder where the fault occurred becomes saturated, and this is something expected because this feeder will carry the total of all the currents coming to it from the bus bar and the outgoing currents through it. To address the fault, measure differential and restraint currents 6 kiloamperes. Plotting this on the differential curve shows the point above it, indicating a trip signal will open all circuit breakers. If a transformer saturates, will the bus bar trip? Here, both values are 600 amperes. This point falls below the curve, meaning the relay stays stable. However, the relay will issue a warning signal called the This means the bus bar will issue a trip signal to open all circuit breakers linked to this bus bar because of an external fault that caused saturation limits for one of the current transformers considered false. If saturation occurs, will lead to a trip decision. Applying this, the point falls below the curve, keeping the relay stable even if a transformer saturates normally. Here, the relay issues a warning signal called the differential current alarm. 600 amperes, and the value remains 600 amperes. Applying this point, it falls below the curve, keeping the relay stable even if a transformer saturates. The relay issues a differential current alarm for prolonged small differential currents due to internal or external issues. It can block differential protection. If the CT's secondary circuit opens during maintenance, will the relay trip? Modern relays detect any CT circuit opening. This alarm triggers with small differential current for long, caused by an internal or external issue. The relay can block differential protection. If the secondary circuit of the CT is opened in maintenance, will it trip the circuit breaker? Modern relays detect CT circuit openings. An open CT circuit increases differential current, causing false relay operation. Opening the CT secondary circuit creates high voltage. Any opening in the CT circuit. If the CT circuit opens, it increases differential current, causing false relay operation and high voltage, affecting equipment. Open circuit detection must act within 10 milliseconds, blocking differential protection before the relay trips. It should precede differential protection to prevent delays. Some settings allow it to block or just alarm, but it's advised to block and alarm SCADA for security. It significantly affects the secondary equipment, so the open circuit detection must operate instantly and within less than 10 milliseconds as soon as the circuit is opened. It should issue a block signal for the differential protection before the relay issues its instantaneous differential trip. This means that the instantaneous operation of the open circuit detection must precede the instantaneous operation of the differential protection. Otherwise, what is the benefit if it causes a delay? Relay settings can control open circuit detection, blocking protection, or just showing an alarm. For security, block and send an alarm to SCADA. Set a time delay to alert engineers quickly. If open CT signal appears, reset via local HMI or binary input. Some relays auto-reset when values normalize. The algorithm monitors differential incoming and outgoing currents, comparing them before and after the CT circuit opens. Set a time delay for this alarm. The open CT detection algorithm checks differential incoming and outgoing currents. It compares currents before and after CT circuit opening. No major current change 3 seconds before CT opening means open CT detection. The algorithm ensures total incoming equals outgoing currents before one cycle. Some relays reset when current values normalize. The open CT detection algorithm identifies CT circuit openings by checking currents at the bus bar. If no significant change is detected, 3 seconds prior, it's an open CT detection. The algorithm ensures total incoming equals outgoing currents before one CT cycle. It verifies outgoing plus current CTs equal incoming CT before one cycle. It includes a time delay option. If it does not appear that there has been any significant change or increase in the value of the currents at least 3 seconds before the CT circuit opens, then this case will be considered an open CT detection case. This algorithm must also ensure that the set of currents entering the bulb equals the set of currents exiting the bulb before one cycle. It must also be ensured that the sum of the outgoing CT plus the current CT equals the incoming CT for one cycle. It should be noted that this algorithm does not concern itself with the number of CTs connected to the relay, nor does it monitor the state of the CT circuit opening in a dead circuit. It also has an option for a time delay. Some very meticulous engineers say that it is a feature or characteristic rather than a standalone function, as there is an independent function within the relay to continuously monitor the current, which is symbolized by a specific symbol. Its philosophy and specific characteristics will require us to refer to it later, God willing. There are also some differences in the philosophy of detection, where this feature starts to operate if the current value is only between 10% and 110% of the value. If the current value is outside this range, this algorithm will not operate, and the current must also be continuous for at least 60 seconds before there can be an opening in the circuit. I will get to it later, God willing. There are some differences in the philosophy of detection where this feature starts to operate. If the current value is only between 10% and 110% of the value, if the current value is outside this range, this algorithm will not operate, and the current must also be continuous for at least 60 seconds before there can be an opening in the circuit. The open CT algorithm operates if power cuts in one phase. Fails if all phases cut, may trip incorrectly. If the secondary CT circuit opens, the algorithm blocks differential protection. Unresolved means losing protection. Scientists stated, blocks unless future fault. Blocks trips from CT openings only. If open and blocked, real fault forces trip. Exceeding unrestrained current triggers emergency, ignoring rules. Scientists recognize the risk. Open CT algorithm will block differential protection if no fault occurs. If open and a fault occurs, unrestrained current removes the block. If fault current exceeds settings, relay declares emergency, ignoring all rules. Open CT detection works only under normal load, not in faults or overloads. If a real fault occurs, the unrestrained current will trip the differential. If the fault current exceeds the unrestrained current set in the relay settings, this means that the relay has declared emergency, ignoring rules. It will not recognize differential, harmonic block, or open CT detection. Note the open CT detection feature works only under normal load, not in external faults, overloads, or unrush. To recognize open CT detection, it's important to note that the open CT detection feature only works under normal loading conditions and does not operate automatically in cases of external faults, big overloads, or unrush conditions. And the big overload and cases of inrush conditions, the distribution path includes protection zones. For a single bus bar without a bus section or coupler circuit breaker, one CT is installed on each feeder. With a single bus bar and a coupler circuit breaker, one CT is installed on each feeder, plus two CTs, one before and one after the coupler. The CT to the right of the coupler protects bus bar 1 on the left, and the CT to the left protects bus bar 2 on the right. With a single bus bar and a coupler circuit breaker, install one CT per feeder and two CTs around the coupler, one before and one after. The CT on the right of the coupler protects bus bar 1 on the left, and the CT on the left protects bus bar 2 on the right. This setup creates a protection state between bus bar 1 and bus bar 2, dividing the bus bar into two zones, each with its own measurement system. Zone 1 is bus bar 1. 200 amps through the coupler from right to left is positive for zone 1. For zone 2, the same 200 amps is negative. I have established a case between the protection of bus bar 1 and the protection of bus bar 2. Therefore, in this case, the number of bus bars is 2, as the single bus bar has been divided into two zones, each with its own independent measurement system. Under normal conditions, we measure each zone separately, assuming that the current entering the bus bar is positive and the current leaving it is negative. Zone 1 is the area for bus bar 1. Notice in this image that the 200 amps flowing through the coupler circuit breaker from right to left is considered positive for zone 1 because it is entering zone 1, and it is read from the CT located to the right of the coupler circuit breaker. Meanwhile, the same 200 amps for zone 2 is negative because it is considered leaving zone 2, and it is read from the CT located to the left of the coupler circuit breaker. The differential current's vector sum for each zone is 0. If a fault of 9400 amps occurs in zone 2 or bus bar 2, all currents change direction to feed the fault. The vector sum in zone 1 remains 0 as the fault is not there. In zone 2, the differential current becomes 9400 amps, triggering a trip signal for all circuit breakers, including feeder and coupler breakers. When these breakers open, the fault is isolated, and supply returns to bus bar 1, achieving normal conditions. If a fault occurs in the overlapping area between CTs, it affects the entire station. All breakers must open, impacting the bus bar protection zone. The differential current in both zones 1 and 2 equals 9400 amps, representing the worst-case scenario. When the 4 circuit breakers open, the fault should be isolated, and supply returns to bus bar 1. A fault in the overlap of the two CTs affects it, requiring all station breakers to open. The CT placement affects the entire bus bar protection zone. The differential current in zones 1 and 2 is 9400 amps. If a single bus bar with a coupler circuit breaker and one coupler CT is used, this CT serves all bus bar protection zones. How is this done? This means that all the shores in the station must be opened at this fault, although the fault is on bus bar 1, but the location of the CT's installation is what made all the protection zone bus bars affected by this fault. Note with me that the value of the differential current on zone 1 equals 9400 amperes, and the value of the differential current on zone 2 equals 9400 amperes as well, and thus this is the worst possible scenario that can happen in this case. However, if a single bus bar with a coupler circuit breaker is used and only one coupler CT is employed, then in this case, this same CT will be used for all the bus bar protection zones simultaneously. How is this done? In the next episode, we will explain the details of this case, which is actually used in some electrical stations. With that, we conclude today's lecture. Glory be to you, O Allah, and praise be to you. We bear witness that there is no deity but you. We seek your forgiveness and turn to you. We hope to see you again in good health.